Yeah, okay, sure.
So what I'll do is I'm going to go here, click, and then select data, and then add data. And what you are doing is basically so you want to do that point, which is that one and that one. So that one should be that point there. So that one plus the error. Just give me, I need to think about this. So there isn't much error there, right? So I'm going to just scroll this down. So this one is that plus that. That's all good. And I'm going to do the minimum. So this is a maximum here.
Yeah, so this is a max and min slope.
Minimum here. I'm just going to do that. Yep, so we're trying to produce the maximum minimum. And I would like to put these points in here as well. Select data, add data. X value is these.
Yeah.
And then the Y value is still so we're doing the frequency versus
1 over wavelength.
yeah. So I've just added the oranges there. And I go here, select data, add another one. X value is this one here. And the Y value is this one here, okay?
Yeah.
So I added the greens. But I think if I join this green here with this orange there, then I get sort of the lower gradient, right?
Yeah.
If I join the green, no, I mean the gray, and this orange here, then that would be great. So for maximum gradient, this is not really max min. For maximum gradient, I'm going to actually get rid of these, the orange and gray. And I'm going to do, for maximum gradient, I think I need to do this one. With this one, which is this one here. And I choose this one here and this one here. So take a look at this, select data, add, X value is just those two. Y value is these two. Done. Then I get this to this, right?
Yeah.
So I can just click that, trend line. I get another trend line there, okay?
Right. So
that's for the orange. That's for the line of best fit.
Y-intercept. What does that mean? The 13.94.
Yeah, so of course the y-intercept must be 0.
Yeah.
But we're just letting y-intercept to be the y-intercept doesn't mean anything, okay?
Okay. Can we take it off then, or should we?
No, I think we shouldn't take it off. It's just something that naturally arises because of the fact that we deviate a little bit from the.
Right.
So theoretically, it should be like that, right?
Yeah.
But because of some systematic error, we may get actual curve going translated a little bit above, like this. And there arises y-intercept, so but we can just ignore it. If theoretically it goes through 0, we simply read the gradient and we just ignore the y-intercept, okay? Now for the minimum gradient, we will have to take this value. And then for this one, we'll have to take this value here.
Okay.
And then put that in as well into this, select data. X value is simply those two. And the Y value is these. Then you got the gray. Gray is now from there to there. Trend line, display equation and chart. And you can see that this one includes, so we can say this, okay?
Okay.
Velocity of sound, speed of sound, okay?
Yeah.
Is.
Does it matter if you say velocity of sound or speed of sound?
It should be speed of sound, because velocity has got certain direction.
Yeah.
But sound doesn't really have any direction. It just goes everywhere, you know?
Yeah.
And then we take, so this is the maximum velocity, maximum speed of sound. So I'm just going to take that minus 3 to 6.15. So that's 36.28. Difference between these two. So 36.28. Or I can do 326.15. So that one minus this one is certainly lower, isn't it?
So the error is lower.
Yeah, so difference between these two is lower than difference between these two.
Yeah. Why do the errors get smaller and smaller?
The reason is because, like, if we just do the wavelength, it'll be consistent. But if you divide, it's kind of difficult to explain. The simplest way to think about this is if you have, just give me a second. So if you have something like some graph like this, and then you have error bars pretty uniform. But then if you do, this is a y here, this is x here. Well, let's say this error bars is actually sideways. So this is error bar on the x-axis. And if you plot 1 over x, what happens is you get, actually this one is some graph that's like that. And then if you get a straight line by doing 1 over x, what happens is that this error bar is big and this it gets smaller and smaller. It's just some inevitable mathematical feature.
Okay. There's no way to really explain why the errors get smaller.
Well, there is a way to explain it. So you got this one is given by that over that square, isn't it? This is constant, true?
Yeah.
But this gets bigger and bigger as you go to the right. As x gets bigger, this gets really, really big. So this gets smaller and smaller and smaller as you go for higher value of x.
Yeah.
So this is that value, right?
Yeah.
So this is mathematical reason. The physical reason is, let's not go in there. It's going to take too much time. But anyway, so this is the mathematical reason, isn't it?
Yeah.
I hope that suffices.
Yeah.
Now, so anyway, the speed of sound is this, and then plus and minus whatever So you take the difference between these two, and whatever is bigger, we take that as the error, okay?
Okay.
So it's equal to plus or minus 36.28. All right?
Yeah.
So that'll be the error. This will be the
So
plus or
that's
minus.
uncertainty.
That'll be the uncertainty.
Yeah.
Okay?
Okay.
So that's how you found the speed of sound with a
Yeah.
bit of uncertainty, because that's, you can't really say the speed of sound according to our result is 326.15.
Yeah, that's true.
Obviously, that's not accurate. There must be some sort of uncertainty, and that can be calculated using the maximum gradient, minimum gradient.
Yeah.
Now, what is technique 2? Can you show me, can you tell me what technique 2 was?
Yeah. So we got 5 different lengths of straws. So we changed the length of the straw. So one was 4, 8, 12, 16, 20.
Mm-hmm.
Then we blew the straw for like 5 seconds onto a software called Audacity.
Mm-hmm.
And then there was an option of frequency analysis where we measured the harmonics, so like the obvious harmonics.
Mm-hmm.
And yeah, and that's how we calculated. Like
We had
we,
straw,
yeah.
different lengths of straw,
Mm-hmm.
and you blow into it.
Yeah.
Did it produce any resonance?
Do you want me to send you what some of the graphs look like? I don't think I put it on the.
Didn't put it on the Word doc.
No.
Okay. So I'm going to read the method 2 here.
Yeah.
Constantly for 5 seconds. So you, okay. Sound was recorded in Audacity.
Yeah.
So it produces like boom sound, right?
Yeah.
The harmonics were calculated by determining the frequencies of the obvious peaks.
I just sent some photos now.
Okay. On WhatsApp or?
Oh no, on email.
Which one is it?
Oh, it's just there. Oh, everything else. Oh, go down. I'm not there. It's just under
Oh,
everything.
this one. Oh, this one. Yep. Okay. So these are decibels and these are frequencies.
Yeah.
So you got these peaks there, right?
Yeah. I mean, some graphs were good, some were really not that great. I think these are some, yeah.
Okay. So obviously the sound, there are many different kinds of sounds, right?
Yeah.
On the straw. So we need to understand the, so when is this due, by the way?
Friday, so 3 days.
Friday. So again, the difficult part is that we need to understand the physics of it,
Yeah.
how this is meant to give you. So we're going to read about this one,
Yeah.
the procedure here. So we're going to have a look. Yeah. So it's an open pipe, and this is Audacity, is it?
Yeah.
It produces some sound, then it records it,
Yeah.
frequency. The first harmonic, second, third, and fourth, and fifth.
Mm-hmm.
You get that. The obvious peaks are different harmonics of the pipe. So are they saying that you get all these different harmonics at the same time?
Yes.
Can you?
Um,
Because this is going through first harmonic,
mhm.
but this one looks like it's got many different harmonics all at the same
But
time.
our graph doesn't look like anything like that. That's why I don't think we got as many harmonics as
Mm-hmm.
like for different straw lengths, we got different harmonics as well.
Right. Anyway,
We didn't
let's
get all.
read through this. When the air in an open pipe is excited by blowing, standing waves are set up in the pipe. The condition for standing wave in an open pipe is that there must be antinodes at each end, right, like this. This
Yeah.
results in a certain lot of frequencies called harmonics. As illustrated by using the frequency analysis options in Audacity, it's possible to measure the frequency of the first harmonic. That knowing that it has a wavelength of 2L, the velocity of the sound can be determined by using the formula this method.
Yeah.
To get the straw to make a sound blow across its end, the sound won't be very loud, but it should be something like this. Yep, that makes sense.
Mhm.
And what happens is not very musical, but good enough to analyze. Once recorded, you can analyze the sound by selecting plot spectrum in the analyze menu. You get frequency and the decibel. The obvious peaks are different harmonics of the pipe. Okay, so that means you're getting all these different harmonics at the same time. You might naturally think that the lowest frequency peak is the first harmonic, but it isn't. This is because the flow of air across the pipe was such that the high harmonics were excited more than the lower ones. What? The lowest frequency?
Yeah, I didn't really understand what that meant
Yeah.
because I assume it would be the lowest.
You might naturally think that the lowest frequency peak is the first harmonic, but it isn't. This is because the flow of air across the pipe was such that the high harmonics were excited. Okay. First of all, for open pipes, you need to know the equation is frequency is NV over 2L. So if I write this one as V over lambda, what you get is 1 on lambda is equal to N over 2L. So lambda equals to 2L over N.
Okay.
So that means, so I'm going to actually create a cheat sheet again. So this is the length. So length of the straw was?
So 4, 8, 12, 16, 20. And then
4, 8,
12, 16,
12,
20.
like that.
Yeah. And I just converted centimeters to meters.
Yep, 0.04. Now, for frequency, so that will be the frequency. Frequency is, for n equals to 1, frequency is 1 times by velocity of the sound, 343, about that, over 2 times L. So you're supposed to get the first harmonic at this frequency here
Okay.
for 4 centimeter and that, okay?
Yeah.
So that's also that second harmonic, 2V, so 2 times by 343 over 2 times by that. So you get something like that, okay?
Okay.
Now I'm going to copy this. Okay. There's someone playing flute.
My brother. Do you want me to go to another room?
That's okay.
Okay.
So this is going to be N.
Yeah.
So we're going to get 7 harmonics there.
Yeah.
So it's equal to bracket that times by V over 2 times by 0.04. So that one there is for that. Okay, all good. And change this one to that one there. Put a dollar sign. Go down. This one is change that to
I think I
that.
got to 8 harmonics.
8 harmonics, is it?
Yeah.
Okay. So we need to complete this one first.
Mhm.
So we can do 8 here. So let's put a dollar sign there. And for the 8, it'll be 8 times by 343 in the bracket. 8 times by 343 divided by 2 times by, no, it'll be 2, yeah, 2L. So 2 times by the L there. Scroll it down.
Yeah.
So these are all the frequencies.
Mhm.
We can convert this into lambda. Obviously, lambda is 2L over N.
Yeah.
So 2 times L, put a dollar sign there, over 1.
Mhm.
So that's the wavelength. And that makes sense because if I times this one by this one, that's frequency times by wavelength, that's the velocity, isn't it?
Yeah.
then I get exactly this.
Right. Yeah.
Okay, so I can also just calculate all of these by dividing this by the speed of sound. So that was 2 times by this divided by that. So 2 times this divided by that. Put a dollar sign there. No, that's not right. Hold on. No, no, no. I have to do that. What did I do wrong? I'm just going to do speed of sound 343 divided by this. Okay.
Okay.
So these are the wavelengths.
Okay.
Now, when we look at your result, okay, so let me read the method here now.
Yeah, sure.
The 4-centimeter straw was blown constantly for 5 seconds. The sound was recorded in Audacity. The harmonics were calculated by determining the frequencies of the obvious peaks. So here's the thing. You have some sound, you have some frequency, right?
Yeah.
How can you figure out the harmonics? See? That's the most difficult part. You know how in the previous section here as well, we had to figure out the N. N was very difficult. We kind of used the cheat sheet to figure out the N, right?
Yeah.
So in the same way, we have some sound, but we don't know what the N is, right?
Right. Yeah, we don't know.
That's why we need this one. All right. So
Yeah.
so let's have a look at your results. So you have this result here. Oh, that's technique 1, right?
Yeah.
And you have this result here. So with the 4-centimeter, frequencies of the harmonics. Graph 1, graph 2. What's graph 1, graph 2? Are they just 4 different
They're
triangles?
like tiles, yeah.
Okay. Let's compare that with this one here. Okay, so for 0.04, 4,000, 8,000, but you got, that's pretty close. Fourth harmonic, okay, in the normal. Let's compare that with 8 centimeter. So that's what we get for the 8 centimeter.
Yeah.
Is that pretty close? Yeah, that's right. That's good. That's pretty good. That's pretty good, right?
Yeah.
You get that, that. that. Yeah, they're all pretty good. And so 8 is really good, but not 4. And it's quite expected because 4 centimeters is such a short thing.
Yeah.
And there's expected to be a lot of error for that. For example, you know, the 4 centimeter, when you hold it, like a little bit of squeezing of the 4 centimeter is going to have huge impact.
Yeah, that's true.
Yeah. So it's influenced by more even slight subtle change.
Yeah.
So if we look at 12 centimeter, let's compare that with the result. 12 centimeter, this one here. So you start from here, right? That one and that one. So this is not the first harmonic.
That's
So
not the first one.
this is not the first harmonic. This has to be shifted to the right.
Okay.
So that's the first. That's the second, isn't it?
Yeah.
So
So
this.
how do we say we knew that was the second? And
We
like
don't.
we didn't see the
There
first.
is a way. There is a way, because have a look at this. So this is how you figure out whether it's a first harmonic, and second, etc. You see how this is this times by 2 is about that, right?
Yeah.
This times by 3 is about that. This times by 4 is about that, isn't it?
Yeah.
And that's how you know this is the first harmonic. 3820 times by 2. Yep. Times by 3. See? Times by 4. See that? That's definitely first harmonic. Is this the first harmonic? Yes, it is, because this times by 2, this times by 3, this times by 4, this times by 5, it's all working, right? So you got a very, very good result. This one, so 2,703 times by 2 is not that.
Right. Yeah.
Right? This times by 3 is not that.
Yeah.
Times by 2 times by 3, right?
Yeah.
So if we assume this is F2, so divide this one by 2, okay? So 2703. I'm going to assume that this is F2. And then you figure out F1, okay? So here's how you do it, okay? Assume. So for length is equal to 0.12, assume F2 is, so 2703 is not F1. So for this, assume F2 is 2703, then F1 should be half of this one, right?
Yeah.
Because for the open pipe, you need to know that N is going to be 1, 2, 3, 4, 5. It's going to be like that. For closed pipe, it's 1, 3, 5, 7. See that?
Yeah.
That was for the technique 1. This one is technique 2, because it's an open pipe.
Yeah.
So you need to know that second harmonic is 3 times the first harmonic.
Yeah.
For technique 1. And this is 5 times that, okay?
Yeah.
So if we assume that in this case, F1, F2 is that, and F1 is 1,350, something like that, you know? Yeah, so this is 1,351.5, okay? Times it by 2, do we get this? Yes, we do.
Yeah.
Times it by 3, do we get 4,000? Yes, we do. Times by 4. We're supposed to get this one, but we didn't. Times by 5. Then we get this one. So this is actually the fifth harmonic.
Right.
This is the fifth harmonic. This is third harmonic, second harmonic. This is 1, 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. They're all correct.
Yeah.
So you didn't get the, so if I do this one times by 6, you know?
Yeah.
So I think it's 6, number 6 here. 7. 8. Yeah, that should be 8 here. 9. Yeah, this is 9. Now, Aspini, technique 2 is a lot better, I think.
Technique 2.
Yeah, because you're getting a lot more data points, right? You're getting a lot more harmonics,
Yeah.
all at the same time.
Yeah, that's true.
Right? All at the same time. And it's easier to figure out which one, what the n is for each one of those.
Yeah.
Isn't it?
Yeah, it is much easier.
Much easier to figure out the ends. But for the, we don't actually need this cheat sheet for this one. So obviously this is not going to be the F1. So we divide this one by 2. Times by 2 is this. Times by 3 is probably that, right?
Yep.
Yep. Times by 4. So it was a 1, 1, 2, 3.
Yeah.
Times by 4. Times by 5. Times by 6. Times by 7. Times by 8. Yeah, so roughly, you know, it's working. So this is 2, 3, 4, 5, 6, 7, 8, 9. If I divide this one by 9, rather than dividing this one by 2, that gives you a bit more average value for the first harmonic.
Yeah.
So if I do that, so 1050 times by 2, then I get this. Times by 3. It's more accurate, isn't it?
Yeah, it is.
Yep. 5, 6, 7, etc. So it's not always this one divided by 2. You can do this one divided by 3, or this one divided by 5, or this one divided by 4 to get the first harmonic.
Yeah.
All right. Anyway, so I think this is the number 1 because it's double, right? 2, 3, definitely 4. 8 times by 5 is about 40.
Yeah.
Yep, I think that's 6, right? 7, 8 there. So what you need to do is identify which one is 1, 2, 3, 4, etc. For each one of those, and then you will have to take average, right?
Yeah.
Yeah. So you can't take the average of them unless you identify the. You got to do the n with n1 with n1, right?
Yeah.
Etc. So I think this one should migrate to here. That's right. This one should migrate. So you got. I'm just gonna ignore that.
Okay.
Or you can put another
Column.
column there. That's 1. That's right. Okay. Now moving on to this one. That's all fine. This is fine as well. This one should move, right?
Yeah.
This one should move as well. And this one's fine.
Yeah.
etc., etc.
Yeah, I can fix those.
Yeah, you can fix that later. I'm gonna do some table. So I haven't done any table here, right? I mean graph.
No, I haven't done the graph.
So I'm gonna assume that this table 1 is the average, okay?
Okay.
Yeah, let's say these are the average. You can fix it up later, right?
Yeah, sure.
And yeah, that's a lot better. That's 2, that's 3, that's 4, that's 5, that's 6, that's 7.
Yeah.
Like that.
Mm-hmm.
So we want to do frequency versus wavelength again, right?
Yeah.
Okay. So what we have there is, again, we've got two equations. One is F is equal to NV over 2L. Another one is 1 on lambda is equal to N over 2L. So lambda equals to 2L over N. So we got this equation and this equation.
Yeah.
So you can figure out the lambda based on the L and N.
Will L be the length of the straw?
Yeah, that's right. Yeah, I think the piano is a little bit distracting.
Oh, sorry.
So I'm going to,
To another room now. He's playing piano. I'll move back.
okay. So what you want to do
Mm-hmm.
is write so the wavelength is given by N over 2L over N.
Yep.
2L over N. So for these frequencies here,
Mm-hmm.
the wavelength was 0.04
Yeah.
times by 2, because for that frequency, this is the L, this is the N.
Yeah.
So if you do that, sorry, this must be 0.4, that's 2, right?
Yeah.
That one there, so
I don't understand, why is the wavelength not fixed?
Oh, wavelength.
Fixed for,
Wavelength depends on the length
yeah.
and the harmonic.
Uh-huh.
So if
So
you
for
have,
every single length of the straw, the wavelength's different?
yeah,
Or?
that's right. That's right.
Okay.
So because you have the straw, and this is the fixed length, right? Let's say
Yeah.
4 centimeter, and you may have the first harmonic that goes like this.
Yeah.
I'm not sure if this is the first harmonic. Hold on. And then you may have something like this. Now compare these two. Here,
Yeah.
the wavelength is very long. From
Yeah.
there to there. This is the wavelength.
Yeah.
So this is for, you can see that 2L is the wavelength, right?
Yeah.
Because it's over 1. This is
Mm-hmm.
the first harmonic. So this is n equals to 1. So you can
Right.
see, because the formula is 2L over n, because it's first harmonic, lambda is 2L. As you can see, this is the L, right?
Yeah.
And the wavelength is 2 times the L, right?
Yeah.
For n equals to 2, we have lambda equals to 2L over 2, you see?
Oh yeah.
So
Yeah.
you see the wavelength is from there to there, isn't it?
Yeah.
That's one wavelength, so it's true.
Right.
So that's why even with the fixed straw, if
They
you have
have,
different harmonics, then the wavelength changes.
okay. I thought
Okay?
the wavelength was fixed for the length of the
Yeah.
straw.
So this is the wavelength. This is the frequency.
Yeah.
So when the frequency is this was the wavelength. When the frequency was this is the wavelength. Okay. So when you actually times them, you get the speed of light, speed of sound.
Yeah.
Okay.
Okay.
Yeah, but for we have to do this one as well. 0. These are the frequencies,
Mm.
and the wavelengths are. So these are the frequency,
Yeah.
and this is the wavelength. So the wavelength is again 2L 2L over n, right?
Yeah.
So move that along like that, okay?
Mm-hmm.
Sorry, this is equal to, this was supposed to be, I want to fix there. So it's 0.08. And then we scroll it down. These are the wavelengths, okay?
Okay.
So I'm going to put this like that, okay? So I need to plot it, right?
Yeah.
So I'm going to actually do this in a block, like, it's a little bit hard to, yeah, I think we should do this cleverly. It's quite complicated. So all I want is wavelength and frequency, okay?
Yeah.
So the wavelength is 0.2 times 0.04 over um, so that's 1, 2, 3, 4. 1,
Yeah.
2, 3, 4, 5, 6, 7, 8. And then I do 2, 3, 2 to 7,
Yeah.
like that. And this is 2 to 8.
Mm-hmm.
And then this is 1 to 8, right?
Yeah.
Now, it's a little bit complicated. So frequency, so it's going to be a bit painful. Just have to do it like that.
There's no other easy method.
Yeah, just have to translate. Of
Yeah.
course, if you're good at programming, there's a way to do this, but I think
Yeah.
just have to, because it's easier column-wise, you know?
Yeah.
It's just that your data was originally, and then for 16, that's 2. It doesn't take too long, you know?
Mm-hmm.
Once it's done like this, then it's easy. 1, 2, 3, 4, 5, 6, 7, 8. Okay?
Yeah.
And then you delete that, and then you get the wavelength. So I'm going to move this one, actually. Actually, the length was 0.04, right?
Yeah.
Scroll it down here. 0.08. Scroll it down. 0.12. Scroll down. And was it 20?
Yeah. 20.
Do it like that. And then what you have to do is just figure out the wavelength, which is 2 times L over 1. Then it's really easy.
Yeah.
There you go. So you get all the wavelengths. And do 1 over the wavelength, which is 1 over this. So we're not having all separate plots for all these different lengths.
Yeah.
Whatever result you got here, these are frequency of the sound, and you get the wavelength of the sound, right?
Yeah.
So all you need to do is just do the frequency versus the 1 over wavelength.
Yeah.
Let's see what we get. We get a straight line.
Yeah.
Quite nice, isn't it?
Mm-hmm.
And then let's see if this is so frequency. So we have to actually swap the
Yeah. Frequency and wave.
yeah, frequency and wave. So select data, edit, X values are the wavelengths, Y values are the frequencies. Once we do that, it will be flipped. Add trend, equation and chart. Oh, there you go. Look at that. 330.
Yeah, that's very close.
There you go. So that's how you do it.
Okay.
So do you think you can do it yourself?
Yeah, I think I can. I'll do it with the averages. This is just for graph 1, so I'll do the average.
But you don't have to do this graph for graph 1. I just didn't use your average. The reason is you don't know which one is, like N1,
No, that's
N2,
okay.
right? So
Yeah.
what you have to do is you have to fix the graph one here like this,
Mm-hmm.
and just make sure you take the average of that and that and that and that.
Yeah.
You should not be taking average of something that's not
I don't
close.
take
Yeah.
average of in between the different harmonics.
Yeah, so you should not be taking average of, like, for example, this one and like this one,
Yeah, no.
right? Yeah, yeah. So I don't think, so I think they're all fine as long as you move. Yeah, just have to move these guys, right?
Yeah, I think I just have,
They were all pretty similar.
yeah.
So once you get the average of it all and they're all in the correct position, then you can just replace this one
Yeah.
with, yeah, with the average. Then you
Mm-hmm.
get this graph and you get the speed of sound. So that's pretty much it.
Okay. Yeah. I think I think I can do it from
Okay.
there.
So let me know if you want the recording of this.
Yeah, I think I do. Yes,
All
please.
right. I'll send it to you later.
Okay. Thank you.
Bye.
I just had one question. Sorry.
Yep.
In the task sheet, it said to give a detailed explanation of the measuring instruments. And for technique number 2, I
Mm-hmm.
wasn't sure what a measuring instrument would be.
What would be the Audacity?
So would I just say it's Audacity or is there anything else?
So what's
Or,
the question again?
wait, let me just get the question.
Comment on the accuracy.
Wait. So in the method, including table of variables section, it said include how variables were measured, controlled, and details of the measuring instruments, including limit or reading.
Maybe I'll answer it over the chat. Okay.
Oh, chat? Okay, sure. Thank
Over. Do you have WhatsApp?
No, I don't. I have Skype.
You have Skype.
Yeah.
Maybe just either use your mom's phone,
Okay, yeah.
or you can just download WhatsApp on your phone, and then
Okay.
you can save my number, and then it'll automatically you'll be able to send a message to me.
Okay. Yeah,
Can
sure.
you do that? So my number is this.
Okay. I think my mum has your number anyway.
Yeah, so save this on your phone, then you'll be able to send a message to me.
Okay, sure.
So now I'll just answer it over the chat, okay?
Okay, sure. Thank you so much.
First, just try to get this result done,
Yeah, yeah, definitely.
and then we have to do the discussion. All right.
Yeah. Yeah.
See you next time.